So I'm not going to go too long into this because I think I'm going too fast. So let me just give you an introduction, maybe an example of factorings. It's going to come together now, everything.
Question.
Sure.
In the book I was trying to read about, I forget exactly what, but it used the word domain just in general. What does it refer to? Because whenever we use the word domain, we use the integral domain.
Do you have your book with? Do you have your book with you?
I have it with me.
Okay, show me right after class, and I'll be able to dig through it and read it. We usually use integral domain, so my guess is that they might be using it for maybe principal ideal domain. They might be using it for something else.
It was strange because they were talking about integral domain, and then they used the word domain, and why. We never discussed it, and I wasn't sure what it referred to.
Yeah, I'm not off the top of my head. That's not standard. That's not standard.
It sounds like a normal domain to me, what they have.
Okay, let me take a look at it, because that's not standard. So if I have a ring and I have an ideal, your analog for ideals are that ideals are like the cosets. The ring is like the group. And you have an element A. We can talk about the element A is congruent mod I to another element B if B minus A belongs to I. This is, we write it like this: A is congruent to B mod I. This is a abstraction of the idea of congruence mod N in Z. That's all this is. So just like the group Z3, you can take all the integers in Z and box them up into 3 boxes, 0, 1, and 2. You can do the same. You can refer to this, and in fact most abstract algebra books start like this. They have you look at equivalence classes with congruences. So you can take all the integers that are 0 mod 3. That means that you can divide them perfectly by 3 because n minus 3 is n minus zeros are divisible by 3, right? So then you can put them all into this box. Anything that's congruent 1 mod 3 goes into this box, and anything that's congruent 2 mod 3 goes into this box. It's the same thing as looking at the remainders when you divide by 3. Exactly the same concept. So now you're going to abstract this, and instead of modding by an integer, you're going to be modding by a whole set. And this is the definition of what we mean by modding by that whole set. So when I write this A congruent to B mod I, that will also generate distinct boxes. So I can take the entire ring and slice it up into distinct boxes. We call that a partition. So when you have Z and you mod by 5, and you're looking at the congruence classes modding by 5, you'll have 5 boxes, and if you union up all those boxes, you'll get back Z itself. And each of those boxes are distinct. They don't share any elements among them. So I'm going to show you an example in a second. I'm giving you all the crazy definitions. So the I is like the cosets. So the collection of all these different equivalence classes are like the different cosets, and those boxes are the things that we call the elements of R/I. How do we add the two? We add the two by adding in front the R and the S, just like we did with cosets. And multiplying is like an abstraction of the addition from cosets. So it's the same kind of formulation, and the I is like the cosets. So I'll show you a specific example, and it will become very clear, I hope. So let's take Z12, and I equals the cyclic group generated by 3, by addition. Let's first find all the elements in R that are congruent to 0 mod I. So I'm using straight the definition I just gave you 2 slides ago, which you probably didn't have time to digest yet, but if I take an A in Z12 and I want it to be congruent to 0 mod that set, this is my I, this is what I is expanded. That definition says that A minus 0 has to belong to this I. Well, that means A has to belong to I. Well, that means A has to be either 0, 3, 6, or 9. So equivalence class number 1, the things that go into the first box are 0, 3, 6, and 9. Good? I'm going through this a little slow because it's weird. Okay, now I've changed the whole thing to 1. So if I change it and say, what is what are the elements congruent to 1 mod I? Well, those are the elements where A minus 1 has to belong to I. This is the definition right here. So A minus 1 belongs to the cyclic group of 3 means that, well, 1 could be added straight into the cyclic group of 3. So A has to be either 1, 4, 7, or 10. Good? That's equivalence class number 2.
They look like cosets.
They are. They're like cosets. The equivalence classes are like cosets. It's exactly the same thing. All of this is just trying to do what we did with normal subgroups. We're doing it, instead of normal subgroups, you have a ring now, so you have an ideal instead of a normal subgroup. Same idea. 2, what are the elements that are congruent to 2 mod I? Well, those are the elements A, such that A minus 2 belongs to this I. Well, those are going to be these guys right here. So equivalence class number 3 turns out to be this thing right here. Look, it does all the same things that cosets do. When you do this, when you guys already did this with cosets. When you did this with cosets, what you noticed is, how do you know you're done? Well, you union up your cosets, and you get the whole thing. Union up these 3, what do you get? Z12. So I get R back. They partition R. What is in R slash I? Well, it is A, B, and C, which you can express as this was 0 plus I, this was 1 plus I, and this is 2 plus I. That's the way they're writing it in the formulation in your book. Those are the elements of your factor ring. Just like the elements of your factor group or cosets, the elements of your factor ring are these equivalence classes. Well, if I have my elements, I can make the addition table. It's the same old thing. The A, the B, and the C go here. Adding by 0 does nothing, so I already can fill in that part of the table. And the addition works out just the way we did with cosets. The inside gets filled in by 1 plus 1 is 2. 1 plus 2 is 3, but I'm working in the cyclic group of 3, so mods out to be 0. 2 plus 2 is 4, which is 1. And then 1 plus 2 is 0. So we're here. So this is the Cayley table I get when I do the addition. So I can do the same thing with times. Times, you always have zeros with everything because 0 times anything is 0. I should have put a little time symbol right here. Sorry. Sorry, Blas. There should be a time symbol in there. And this is what I get. Same kind of manipulation, right? How do I do this? 2 times 1. How do I do this? 2 times 2, which is 4, which is really 1. Okay, clear? I told you it's almost like you had to see this first to understand why all the other pieces were coming into line. They're all here to make the factor ring. Or it might be called quotient ring in your book. I'm not sure. So I gave you these.
Is it true then that cosets are always equivalence classes? Or there are some exceptions?
No, for the rings you'll get that, but the cosets are not. Let me think about that. Yeah, you can do exactly the same thing I did here. You can think of. In fact, I said that to you when we were doing cosets. The coset addition, you're actually modding by the subgroup, right? It's exactly the same thing. Exactly the same thing. Yes, it's a partition and it's their equivalence classes. And you're modding by the coset and the subgroup. So instead of I, you would be modding by N. Same exact definition. So these are, I took your R to be Z24, and I just gave you a few to run through. It's just, it's one of these useful exercises like doing 200 integration problems. You learn how the integrals kind of work after you do 200 of them. Same thing. It's not bad once you do it. It's doable. Okay, any questions?
Question about the dimutual group and the SN, they would be considered a ring.
No, because you don't have multiplication on them.
You don't have addition.
You only have, well, you have an object that's called, you have a group
Right.
with addition. The composition is addition, but I haven't defined a multiplication on it.
The same would apply to the quaternion, right?
The quaternions, I think you can, because you can express them as matrices, so you have matrix multiplication. But the braids you can't.
What about addition?
I'm not sure, yeah. I'm not sure.
Multiplication is fine, just addition.
Right. Well, it is your group, it's your addition under, it's whatever your binary operation is under addition for groups, right? You have that, but you don't have the multiplication, the distributive law, you don't have those pieces.
Because I mean, I was just using that as an example. I was thinking about ideals of like, is it proven? I don't think any of the subgroups can be formed in ideals. Because you get something out of not an element of I.
You can make, if you want to get good examples, you can make good examples by taking something that's a known ring and just extending it by one element, like the Z of I. Then you get some funky examples.
So we're essentially dealing with numbers now, as opposed to abstract, things.
Well, I think the polynomial rings give you some really strange things that, but they extend better from what you know from the number system. You should have felt familiarity with some of the theorems that are coming, right? And many abstract algebra books start first with rings and fields, even though algebraically that's not the progression, right? You want to build up your algebraic structure. But the idea is that a student who's familiar with these ideas will see the rings and fields and feel more comfortable with them. But it's a lie, because they're going to abstract sometime, right? Yeah. So sometime, somewhere, somebody's going to come, wake up, there's something new. So I don't know, to me it's more pretty to see it building. Okay, any other questions? Certainly it's interesting which groups, additive groups, can be tagged on a multiplication. I never thought about I never thought about braids if they have a multiplication that you can define on them. Never thought about it.